Hello, I think I'm live. I'm sorry, I had some problems with my network, so I managed to fix it, hopefully. Okay, so I'm not sure, maybe, so I hope I won't have any interruptions, but I also have my phone nearby, and those who have me as friend on Facebook can write me maybe on the Facebook Messenger if I have problem with the network connection. I think the live video will end abruptly. So yeah, I hope it all works fine. But yeah, if I'll probably keep talking and not going back to see the status. And if you find that I'm not online, just yeah, let me know that something happened, so I don't talk just to myself. So yeah, I'm sorry for the delay. I'll try to present everything in the time until 18 o'clock. So let's start. So today I wanted to discuss about distributional semantics, word embeddings, and two neural architectures that can be used to produce word embeddings, the Skipgram model and the CBAU models. And we will continue the discussion in the next lecture on the same topic. So first about distributional semantics. So this is the main concept used to obtain word embeddings. So the main idea is that we want to have some vectorial representation of words, and we use this assumption that words in the same context have some, if they can be used in the same context, they have some similar meaning. So this will allow us to compute the similarity of words. Okay, so this can be used in various contexts. So for example, one application could be in question answering. So if we have a question such as how tall is Mount Everest, we can figure out that the word tall refers to height, and we can choose, I don't know, the answer that refers to height and not an answer that refers to something else about Mount Everest, or I don't know. Okay, so and this also has applicability. So this was question answering. It can also be applied in plagiarism detection. So similar words can be used to replace other words to seem that the text is not the subject of plagiarism. But if we have a model to measure the similarity between words, we can also use it to measure the similarity between texts. So here we have some an original text and one that is plagiarized after this one, that has some changed words, and here with red we have the words highlighted that are have a similar meaning. So in a vector space we can measure this similarity with I don't know, let's say dot product or cosine similarity and so on. Okay, so what we have here is that yeah, in one way to obtain this similarity is to use dictionaries that are also called thesauri. So yeah, the problem is if we want to use dictionaries or any knowledge base that is manually built by, let's say, linguists, Well, the problem is that word similarity can change over time. So we have here some examples of word use that have different semantic, let's say, meanings. So the word dog over the years has broadened its semantic meaning, while, for example, the word deer or hound reduced their semantic meaning, and they are less used. And also one example is the word gay, which the first sense means happy, and in the 50s it meant talkative and so on, and now it has a connotation that is related to a gender preference. Okay, so the problem with such methods, if we want to build these dictionaries with word meanings, that over time they can evolve, so they can change the meanings. So for example, for historical linguists, they are actually saying that we need a dictionary or a thesaurus for every year. So it is labor intensive to produce this data manually. So an alternative approach would be to compute these word vectors automatically, and to be able to compute similarity between words using these automatic representations that can be constructed from data. And the main direction here, so all the ways that we can do this are based on unsupervised models. So we just need to collect the documents. We don't need any annotation. So this is possible because we are based on this concept that similar words should have identical environments or identical contexts. Okay, so for example, we expect that words that are synonyms, oculist or eye doctor, occur in almost the same environments or almost the same context. So I'm saying I'm going to have an eye control, and I'm going to the eye doctor, and I can say the same thing and refer to an oculist. And if I gather a large collection of documents where I can find these two words, I expect that these two words will appear in very similar contexts and similar phrases. So judging from this, that they appear in similar contexts, we can say that these words are semantically related. So we don't need any annotation. We just need a big collection of documents to obtain this similarity. Okay, so the main goal is to, if we obtain this similarity, then when we build this vector space model, we will obtain representations of documents that not documents, representation of words that are close to each other if they have similar meaning. So we can notice, I don't know, groups of in the vicinity, for example, groups of fruits. Then if we enlarge this vicinity, we obtain a group of different foods, and then other things. Okay, so my connection seems to be all right. Okay, so yeah, the intuition here is explained with a word here that is borrowed from a different language. So I think it also has a translation in Romania, which is Tescovina, so we know what the word means. So if we don't know what the word means, let's assume that we don't know these words, and if we just look at the context, we can figure out that this is an alcoholic drink, right? So we have here a bottle of Tescovino. Tescovino makes you drunk, and we also know that it's made out of corn. So even if we don't know what the word means, from different contexts we can learn more about this word. So it means that for people, just by looking at the context surrounding the word, they can figure out what the word means. Perhaps not from a single context, but if you gather a lot of contexts in which the word appears, you can figure it out. And this also is the intuition of the algorithm that builds vectorial representations of words. So in the end, we want two words to have a very high similarity score if they have similar words in context. So this is the main intuition. And there are various kinds of models that can be constructed through various approaches. So first we will discuss about some handcrafted approaches that are based on word co-occurrence matrices and term document matrices. And then we will discuss about dense vector representations. And here we can also use a shallow approach like singular value decomposition, but we can also build neural network models like Skipgrams and CBAW. And there is also another way to obtain word embeddings by constructing actually word clusters. So it's instead of um, using this maybe continuous space that can give you some measure of similarity. In Brown clustering, you just determine some hierarchical clustering of words, and you can use this as a similarity. But we will not cover this in our lecture because it's not really related to deep learning. So actually, yeah, the only deep learning concept here is the neural network inspired models, and we want to gradually work our way towards these models. Okay, so the shared intuition for all these approaches is that we want to model the meaning of a word by an embedding in a vector space. So for each word, we will assign a vector of numbers, and we call this vector of numbers embedding. So then when we build this vector space for words, it is also called an embedding space, and each word has a corresponding embedding in this space. Okay, so first we discuss about words and co-occurrence vectors. So this can be actually there are two main approaches in this direction. So we can use term document matrices or term matrices, and the first tells how often a word occurs in a document, and the second one tells how often a word occurs in the same context with a different word. So in the first approach, in the term document matrix, we have here an example from plays by Shakespeare and words that appear in these plays. And if we look at the different plays, so these are about emperors and so on. So they have the words battle and soldier that appear more often, while these are have the word fool and clown that seem to appear more often. So then if we look at each document, we see that we obtain a bag of words representation here. So each row is a bag of word representation for the document. So then if two documents are similar, they should have similar bag of word representation. So in this case, making, I don't know, computing a scalar product between these two columns is higher than the other two. So it means that these two are more related or more similar than compared to the other two, and these two are also related to each other because of the words fool and clown. And the same can also apply to words. So if two words are related, their vectors should be similar. So here the words fool and clown are related because their vectors are more similar, and the same we can say about the words battle and soldier. So yeah, this example contains only 4 words and 4 documents, but these matrices can be very large, and also many of the components are 0. So the matrices are sparse. So this is why these type of models are called sparse models. Okay, so we also have the alternative approach is to compute word or word context matrices. So instead of entire documents, we just use small context. So for example, this can be paragraphs or windows of around 4 words, something like that. And now a word will be defined as a vector of counts of context words over, so just count how many times it appears in the same context with other words. So instead of each vector being of length d, which is the number of documents, now each vector is going to be of length v, which is the size of the vocabulary. So the size of the word matrix is the size of the vocabulary squared, so it's a square matrix. And here is one example. So the word matrix here with sample context of 7 words. So here we have the word, the target word that is listed here on rows, and then we look at the context and we put 1 wherever we see a word from the same context. So here we have pinch in the context with apricot. For pineapple we have also pinch somewhere. Well, maybe it's not shown here. So yeah, these are, or maybe we have sugar. We have sugar here. And yeah, for computer and digital information, we also expect words from the same areas. So when you compute the similarity between these word vectors, we also obtain a similarity between a semantic similarity between the words that we compare. So here we see that apricot and pineapple have similar vectors, and the same can be said about digital and information. So this should be more connected. Okay, so this was only a small example, but in reality, the vocabulary, the number of words can be 50,000 or around 50,000 or even more. And a real matrix would be very sparse. So many of the words that appear in the document, they usually appear only with some of the words, not all the documents. So many of the values in this matrix will be 0. But this is okay since we have efficient algorithms for sparse matrices. Okay, so here another aspect that should be considered is that it seems that shorter windows cover a more syntactic representation of the documents, and longer windows go towards a more semantic representation of the word embeddings. So yeah, depending on the task that you want to solve, you can also choose the size of the window accordingly. Okay, so here we also have we can distinguish between two different kinds of co-occurrences. These are called first orders or syntagmatic associations. So these are typically nearby each other. So for example, we expect wrote. So wrote is a first order associate of book or poem or other things that can be written. And second order co-occurrence or paradigmatic association is wrote is a second order associate of words like said and remarked. And so these usually have the same words in context, or for example, yeah, but so it's not directly linked, so they do not appear together in the same context, but in their own context we can have similar words. Okay, so we discussed a lot about measuring similarity, but we didn't discuss about how we compute it. So given two target words, V and W, we can measure, for example, the similarity using the dot product or the inner product. So for these two words, we just compute the sum of the products of all the components. So this is expected to be high when the two vectors have large values in the same dimension. So dimension here means the component I. So if let's say V2 and W2 have both have very large values, these are highly correlated, and when we compute the product here, we will obtain a large value. And low or zero for orthogonal vectors. So if we have 0 here for V2 and 0 here for W1, then here the sum will be 0, so even if the other value is large. So this means that these vectors will be orthogonal. So where one has 0, the other has a different value. So these have a complementary distribution and they shouldn't be considered as similar. Well, the problem is also, so the dot product is also proportional to the length of the vectors. So we obtain higher values if the vectors are longer, and also if they have higher values in each dimension. So a vector that is more, let's say, a word that is more frequently used, it will naturally have more the corresponding vector will be less sparse, so the values will be also higher, and essentially its norm the norm of the vector will be higher. So this is bad because when we compute the similarity with this vector, we generally obtain higher similarities. So the dot product is sensitive to the word frequency. So in order to eliminate this effect, we can normalize the dot product with the norm of the two vectors, and this means that we actually use the cosine between the vectors. So in the end, the most common way to measure the similarity between word embeddings is to use the cosine similarity. Okay, so I guess you all know the formula for cosine similarity, so I will not stay too much on it. Just want to recall that when the vectors are very similar, the similarity will be 1. So it means that the angle between the vectors is 0. If the vectors are orthogonal, the cosine similarity will be 0, and if the vectors are in opposite direction, the similarity will be -1. So the values of the similarity is between -1 and 1. Okay, and here we have an example with the word apricot, digital, and information, and these are represented in this matrix with the words large, data, and computer. And so here we have the counts, how many times apricot appears in the same context with large, and so on. So here we expect that the words digital and information to be more similar to each other. So if we just compute the similarity here for apricot and information, here we have correlation. So if we just ignore the norm, here we will have dot product of 2, but when we normalize, the cosine similarity gives us a similarity of 0.23. And between digital and information, we have a higher similarity of 0.58, and apricot and digital are orthogonal, so the similarity is equal to 0. So then we can also represent here the vectors in two dimensions with large and data. So here we have the dimension for large and the dimension for data, and the angle between these vectors also represents the similarity between them. Okay, so there are several ways to measure the similarity between word embeddings. So all these I didn't mention first, but so the cosine similarity is also used to measure the similarity for neural embeddings, and the neural embeddings are also evaluated in a similar way. So there are two types of evaluation. There is just forgot to look here and see that I'm still streaming. Okay, so there is the intrinsic evaluation, which is given by the correlation between the algorithm and the human word similarity ratings. So we can, for example, ask humans to provide the semantic similarity between words. So there are data sets that have these intrinsic evaluation, and they have examples such as this word is closest in meaning to which of these, and the humans have to choose one answer. So then when we build the word embeddings, we can see if the most similar choice here from our word similarity embedding will be the same as the one decided by humans. And in the extrinsic evaluation, we have different tasks like spelling error detection, word sense disambiguation, essay scoring, and so on. And we can use these word embeddings to see how, I don't know, other deep learning models that are trained on top of them behave, on how well they improve in terms of performance. So the word embeddings can also play an indirect role in the performance of neural models that are trained on top of them. Okay, and now we discuss about dense vectors. Okay, so as I discussed previously, we saw that term-term matrices are very large. So they have around, so the matrices are large and the vectors are very long. So the length of an embedding vector can be between 20,000 to 50,000 components. And the vectors are sparse, so many of the elements are 0. So this means that perhaps we can also build a more compact representation. So if many of the elements are 0, can we build a more dense representation in which we don't have 0 components, but still the word vectors are representative? Okay, so the alternative is to learn these vectors. So these sparse vectors are typically computed as I showed before from data. And the alternative is to learn these word embeddings. And this time we can make them shorter and more dense. So these dense vectors can be easier to be used as features in machine learning, so we have less weights to tune. They also may generalize better than storing explicit counts. And they can also do better at capturing synonymity. So for example, car and automobile are synonyms, but can be represented as distinct dimensions. Okay, so first approach to obtain dense vector is to use singular value decomposition. When we apply this approach on the term document matrix, we call it latent semantic analysis. So this is a special case of singular value decomposition. Another approach is to use neural language models. So these are inspired by predictive models. So we'll present the Skipgram and the Seabaum models, which are alternative ways to obtain word embeddings. And as we mentioned before, Brown clustering also obtains dense vectors, but is not discussed here. So first, let's discuss about singular value decomposition. So I'm not going to discuss too much about the details, just to present the main concepts. So we want to approximate an n-dimensional data sets with fewer dimension by rotating the axis in a new space. So in this new space, the dimensions are sorted according to the variance with respect to the original data set. So every dimension captures, so the first dimension captures most of the variance, and then every subsequent dimension captures, just as in PCA, captures most of the remaining variance, and so on. So related methods here are PCA and factor analysis. So the main idea with PCA, for example, is it is used for dimensionality reduction. So we look at these dimensions with high variance. So the first PCA dimension is the one with the highest variance. Then the second dimension is orthogonal and is the orthogonal dimension with the second highest variance, and so on. So in singular value decomposition, this concept is based on decomposing our matrix. So this is a rectangular matrix of the number of words and the number of contexts, and it is decomposed into a product of three matrices. So we have the matrix W. So the rows corresponds to the original matrix X, and here we have M columns representing the dimension in a new latent space. So this will be the embedding that we are constructing. So here these m column vectors are orthogonal to each other, and they are ordered by the amount of variance. So the first column will correspond to the highest variance, and so on. Then we have a diagonal matrix of m by m components, and these contains on the main diagonal the singular values expressing the importance of each dimension or how much of the variance it explains. So the first component on the main diagonal corresponds to the highest singular value with which explains most of the variance, and so on. And then we have the matrix C that has the columns corresponding to the original X, and the rows M corresponding to the singular values. So then when we do the product of W, S, and C, we obtain the original matrix X. So as I mentioned before, here we have on each row corresponds to a word, each column corresponds to a context. So the matrix X has W and or times C components, and here we learn these matrices W, S, and C such that when we compute the scalar product, we obtain the original matrix X. So these dimensions, as I explained before, so here when we multiply the matrices, the dimensions correspond to the original matrix. So this is the basic singular value decomposition, and when we apply it to the term document matrix, we call it latent semantic analysis. And in addition to that, what we do in latent semantic analysis is we just keep the top k dimensions. So since the dimensions are ordered by the variance explaining the data, then we can do as in PCA, we can keep the top let's say 300 dimensions, and this will give us word embeddings of word embedding vectors of 300 components. Okay, so if we just keep only the top 300 dimensions, the result will be a least square approximation of the original matrix X. So as we add more and more components, we'll be able to approximate X better and better, but the goal here is not to obtain an exact approximation of X, but to build these dense word embeddings. So dense means that the vectors are non-sparse and have a low dimension, such as 300. Okay, so yeah, latent semantic analysis looks something like this. So we have the words, the context. So this is the matrix that we want to approximate, and here we just keep the top k dimensions. So basically we eliminate this part from W. From the diagonal matrix, instead of M or M components, we just keep the first k or k components, and for the matrix C we do the same. So if we eliminate these parts, we obtain a word embedding that is more dense. So the dimension here, k, is expected to be lower than M. Okay, so yeah, these are additional information about LSA. Okay, so yeah, as I explained, this was an example with the term word context matrix. So LSA can also be, or SVD can also be applied to word matrices, and the concept is very similar. So when we apply it to the term matrix, we have the matrix X. So this time the matrix is the V or V components. The matrix W that we are building has the same dimension as X. So actually all these matrices are square matrices, and here we have a square matrix. So we can apply SVD on top of this, and as before we can keep the top k dimensions. So this time it means that W and C will no longer be square matrices, and the columns here will correspond to the number of dense components in the embedding vectors. So it's the same idea, and yeah, this is called truncated SVD when we apply it on the term matrix. So the name latent semantic analysis is only when we apply it on term document matrix. Okay, so the embeddings for a word I are the rows in the matrix W. So each row is a k-dimensional representation of a word. K can be set anywhere between 50 and 1000, so this is commonly regarded as dense vectors. Okay, and there are some results in literature that tell us that if you remove the top, perhaps the top 50 dimensions, you can obtain better results. And this is because perhaps these dimensions correspond to words that are more frequent, like stop words and so on. Okay, so here we have the benefits of using dense embeddings in favor of sparse word matrices. So these lower order dimensions in sparse matrices can represent unimportant information. So there the normalization is very important. And also in dense vectors, truncation can help to generalize better to unseen data. So it's also can be seen as a way of preventing overfitting. And for classification tasks, it was definitely easier to use these smaller number of dimensions. Okay, so now we discuss about the neural approaches, which is the so the main approaches in this direction are the Skipgram model and the CBAM model. So yeah, these are just prediction-based models. So they try to predict words in contexts or contexts of words, and these approaches were proposed in 2013, and since then I think this is one of the most and actually also the main breakthroughs perhaps of neural networks in natural language processing. So this paper of Mikolov I think reached more than a few tens of thousands of thousands of citations. So it's become a very relevant paper in the field. Okay, so the main idea is to learn these embeddings using neural networks as part of the process of word prediction. So while we try to predict words in a given context, we're automatically learning these embeddings. So the embeddings are actually the weights of these neural models. So once we train them, we implicitly have the embeddings that we want to use. So it seems that this approach is much faster and easier to train compared to singular value decomposition. And SVD for very large matrices is also can have problem with stability and so on. There are many packages like Word2Vec and fast text and other approaches that give you word embeddings that are already defined for English and other languages, including Romanian. And these models can also be fine-tuned on specific data sets to get improved performance. Okay, so first we discuss about the Skipgram model. So in the Skipgram model, we predict each neighboring word of a given word. So let's say, so typically this is done with a context window of two words on each side of the current word. So the total number of words in the context is 4. And here we use this parameter c to determine the size of the context. So in this example, the context size is 4. And yeah, when we go through the corpus and pointing, so the target word being the word WT, so T here means this is the target word. So in the vocabulary, this word has an index, let's say J, so we can call it here WJ. So what we want to predict, for example, in here is word WT plus 1. So if in the context the target word is at index T, then the next word is at index T plus 1. So if you look in the vocabulary, this word has the index K. So then we can write the task here is to compute the probability of having the word K immediately after the word WJ. So we interpret of the probability of having this word co-occurring with the word J. Okay, so this is the task that we want to solve to compute this probability. And in order to address it, first we can build a one hot vector for each word. So we actually start from these sparse vectors, those one hot embeddings. So we look at the length of the vocabulary, and let's say if the word popsicle is the 5th word in the vocabulary, then the corresponding one hot vector has 1 on the 5th dimension and 0 in rest. So as input, we use these one hot vectors, and similarly as output, we also use these one hot vectors. So these have the size of the vocabulary. So we have 1 on one component, and everything in rest is 0. And here we define this. So this is the Skipgram model. So we have here a neural model with 2 layers. And here we learn some weights W that are multiplied with the input vector WT and projects this word into an embedding layer of dimension D. So this depends on the number of units that we use for this layer. So then this embedding is multiplied with the weights that are learned here, and these weights produce some probabilities for the context words. So we have the probabilities for the context words, let's say WT minus 1 and words WT plus 1. So if so in this example C is equal to 1, but in general the model can have more words in the context. So for each word we actually predict these probabilities, and the target is to predict 1 for the word corresponding. So it's basically we want to produce the one hot embedding for the word wt minus 1. Okay, so here we have the embedding vj that corresponds to the word j from the vocabulary, and this is also equal to the output of the hidden layer h, so, or the embedding. So here the output of the network is determined by multiplying these weights with the embedding h, and we obtain an output. And actually, yeah, what's missing here in order to obtain the probabilities is we are also using the softmax function to transform these outputs into probabilities. Okay, so yeah, so for an element k here, so essentially what we learn in this matrix W is for the word k, we want to produce, so actually, yeah, this component, the output, the pre-softmax output that corresponds to the dimension k, which corresponds to actually word k in the dictionary, is computed as the embedding. So here W, as I said before, it also contains the embeddings of vector k. So actually, sorry, this W contains the embedding of the vector k on I'm trying to, it's d times on column k. Yeah, so this is, I think this is column k, which is, yeah, if I look at the dimensions here, so d is the dimension of the embeddings, and the embeddings, so this is the number of columns. Am I thinking right? Yeah, so rows or columns, v. Yeah, so the embedding is a column vector. Yeah, so this is transposed. Yeah, so here actually, yeah, I recall. So this is the this W, this is the transpose of this W. So here we have WV times D, and here we have D times V. So yeah, so actually this transposed means that this is a row vector and is multiplied with a column vector, and we obtain the output for the word k here. And yeah, this is how it works. So essentially the matrix W of weights contains the embeddings, and for each word in the dictionary we predict an output that should, after applying softmax, will be a probability that is close to 0 if the word does not appear in the context, or a probability close to 1 if that word appears in the context. Okay, so yeah, as I mentioned before, the output is, so okay, so one more observation here. So we multiply the vector of weights with the embedding h. So actually this is the embedding corresponding to the word w j, or in the context wt. So yeah, this corresponds to the embedding of the target word. So here we have the output is actually given by multiplying the embedding of a word in the context with the current word. So what this means is that we want to optimize this embedding through this neural model. So when we jointly optimize them, we want to make sure that the output is high if these two words if this word should be predicted for the context of this word, and it should be close to 0 if this word. So basically, when we optimize the word embeddings, we want to make sure that if the words appear in the same context, they'll have produce a high output, and if they do not appear in the same context, they will produce a low output here. So it means that when we compute the scalar product here, if we want to have lower output, these vectors should be orthogonal, and if they appear in the same context, they should not be orthogonal. They should have some correlation. Okay, so these outputs are turned into probabilities using softmax. So the probability of word wk appearing in the same context as word wj is equal to the softmax function, which is the exponential of the scalar product of these two divided by the sum of all other exponentials for all the words in the vocabulary. So this is how we compute the probabilities. Okay, so actually now we learn two embeddings for each word. So we have an input embedding V in the input matrix W, and yeah, so it's the parameters here are decoupled. So this is a transposed. But it has also its own parameters. So we learn two embeddings, and in practice we can use the sum or the concatenation of the two embeddings matrices to as a word embedding space. Okay, so let me see if I need anything to add here. No, I think it's pretty clear. So yeah, we have embeddings, as I said, from both matrices. So we can use one of them, we can sum them up. So these matrices, if we transpose this one and do the sum, we obtain another embedding, and we can also concatenate them, but this will double the length of the embedding. So just using one of the embeddings seems to be enough in practice. Okay, about the learning, so we optimize using the log probability. So we maximize the parameters of the model with respect to the log of the products of all these probabilities for the words that appear in the context with word t. So we just multiply all these probabilities, and since this product involves probabilities that are between 0 and 1, we use the log to have numerical stability. So this is equivalent to so here we change the, instead of using log of product, we use a sum of logs. So here we use the sum of logarithms. So we just replace this, and here we have the probability of word t plus j, and here j can go from the entire context window. And if we expand this with respect to t. So this is equivalent to using, so we expand the probability here and we replace it with the softmax loss. So we said that this probability is equal to the softmax function. So here we replace the probability with the softmax function accordingly. So we can write it like this, and here we can, the log of a divided by b is equal to log of a minus log of b. So when we separate this fraction as a subtraction, so the first component is log of exponential, eliminates the logarithm, eliminates the exponential, so we're just left with the scalar product of v transpose and v, and here we have minus logarithm of this component, so minus logarithm of the sum of all the exponentials. Okay, so this is the optimization function that is used to learn the embeddings. And now going on to the continuous bag of words model. So yeah, I hope I can finish in time. I forgot to check about the streaming, so it's fine. Okay, so in the continuous bag of words model, so in the Skipgram model, we had one input word and we wanted to predict all the words in the context. So here in the CBAU model, we do the opposite thing. So we take the words in the context and we try to predict the target word. So here the input is a one hot input vector for each context word. We have the projection layer, that is the sum of the embeddings for the context words. So for each word we obtain an embedding by multiplying the one hot vector with the corresponding weight matrix, and then we obtain an embedding. So all these embeddings are summed up, and then from this vector of that contains the sum of all the vectors, we compute the one hot representation for the target word. So for example, if we have this phrase, the cat sat on the floor, and we consider the context, the window size equal to 2, so C equal 2, we have the words the cat and on floor that are in the context, and the word sat that has to be predicted by the CBAU model. So this is called continuous bag of words because these words are aggregated using the sum into a single embedding. So yeah, this is known as the continuous bag of words. Okay, so as before, here we use the one hot embeddings as input. So we have, let's say for cat, this embedding, and for the word on, this other embedding. We learn the matrices W and W prime. Here, when we apply the model, so we have the one hot vector that is multiplied with the matrix W, and we obtain a vector that is the embedding for cat. We sum it with the embedding for the other words in the context, in this case the vector for words, and yeah, we compute actually the average, so we also divide it by 2, so make sure that the numbers are within manageable values and do not depend to the size of the context. So actually we compute the average. And then from this average we multiply it with the um, matrix W prime in order to obtain the output Z, and from Z we apply the softmax to obtain the final one hot vector for the target word that needs to be predicted. Yeah, let's say we obtain a word that is close to y set, so the highest probability corresponds to this word, so it means that the predicted word is set, and that's fine. So as for the Skipgram model, the matrix W contains word vectors. So these are the embeddings that corresponds to the words. So we can, as before, we can either consider W or W prime as the word's representation, or we can take the average or concatenate them, and so on. So we also have time to show some interesting results. Okay, so these are some examples of the nearest words to some embeddings. So here we have examples from the original paper from Mikolov. So we have the target word Redmond, and we have here we see Microsoft. So perhaps yeah, the most relevant thing about Redmond is that Microsoft has an office there, and here we have the name of a president, and we see that the words in context are his first name, and he's related to what's known as the Velvet Revolution, and so on. So we see this these nearest words for proper nouns for different. For example, here we have the verb capitulate, and we see here forms of the same word that are similar. So we have variations of words, and also synonyms like graffiti and spray paint, and so on. We also observe that these embeddings capture relational meaning. So for example, if we go to the embedding of the word king, actually, yeah, maybe I'm going to use this example later. So here, if we take the, yeah, maybe look at the example first. So you can also use this correlation. So if you take the vector for the word king and subtract man and add the woman, you will obtain a vector that is very close to queen. And the same operation can also be applied to different concepts. So for example, you can take the vector for the capital of France, Paris, subtract France, add Italy, and you will obtain the vector for Rome. So this means that these relations are measured by certain vectors in a similar way. So the relation between king and queen is similar to the one between man and woman. Same as here, the relation between walking and walked is similar to the relation between swimming and swam, so different tenses of verbs. Relations between countries and capitals, so the vectors for Spain and Madrid, Italy and Rome, Turkey and Ankara, and so on. So they all seem to be modeled by one direction in the embedding space, not necessarily orthogonal to one of the axes, but a certain direction. Yeah, here we also have types of relationships. So this was observed for capital cities, currencies. So we have this relation. So we have the currencies in different countries. So they are all modeled by the same relation. Cities in states, man, woman, as I explained before, relations between adjectives to adverbs, antonyms, so possibly and impossibly. So there is also a semantic relation between these two, and this relation is also modeled by some direction in the embedding space. Yeah, so this was observed in the word2vec model computed from 6 billion word corpus, or a very large corpus. Yeah, so here we have examples of the capitals that have similar displacement vectors. Big and bigger, small, larger, cold, colder, and so on. So these are superlatives and so on. Okay. Yeah, this is also interesting. So in some cases, you have this copper and the element for copper. It applies to zinc, to gold, but for uranium you obtain plutonium, which is an equivalent to uranium. So yeah, this is not really, so it's an unsupervised model. You can obtain whatever you get in the data, but it still obtains some interesting relations. And you can also find I don't know, interesting things about for example, the representative food for Japan is sushi, and you obtain the equivalent for Germany is bratwurst, for France is tapas. So these are borrowed from Spain. So tapas are typically known in Spain, but French people borrowed and developed many restaurants that serve tapas in France. And yeah, it seems that the representative food for USA is pizza. So this is what the word embeddings tell us. I'm not sure how Americans feel about this. Okay, so this was the last slide. Yeah, I'm going to stay for a few more minutes for questions, perhaps until maybe 5 more minutes, something like that, if there are any questions from you guys. Yeah, so the transmission, I didn't have problems with the transmission, so it seems to manage to yeah, so these are alternative models. You can use either one. So in the end, the goal is to learn some word embedding. It's not there is no clear winner in this regard. So they obtain similar results. Yeah, about this question. So we will see next week. We will discuss about more about word embeddings, and we will discuss about some papers that actually mention and prove empirically that the quality of the word embeddings for previous methods like SVD and neural embeddings are similar in many regards, but there seems to be some benefits, but perhaps not as great as initially thought. So yeah, perhaps nowadays I think that the way to go is definitely to try to use neural word embeddings, but in some regards, you can also use SVD or other approaches. So more on this topic we're going to discuss next week, and you will see some interesting results. Okay, so yeah, just please, so if you have questions, don't wait for me to answer to the previous question. You can just write them down in the chat so I can answer directly and not have any long periods waiting for questions. So I'll probably stay for 1 or 2 more minutes to see if we get any more questions. Otherwise we can finish here. Okay, so it seems that there are no further questions. Thank you everybody for participating, and see you next week with the follow-up on the same topic about word embeddings.